All right, future doctors, welcome. Today we're tackling a chapter that is a goldmine for your NEET prep, thermal properties of matter. We're going to break down the concepts you absolutely have to know, solve some real past-year questions, and give you the strategies to just nail this section. You ready? Let's get into it.
And boom, right away, let's look at a real question from NEET 2021. Seems a little intimidating, doesn't it? A cup of coffee cooling. But don't you worry. By the time we're done here, you'll have the exact tools to solve this and problems just like it, no sweat. Let's build our way up to the solution.
Okay, first up, we've got a topic that, the NEET examiners just seem to love, thermal expansion. And look, mastering this isn't just about memorizing a formula. It's about really getting a feel for how stuff behaves when it heats up. It's a concept that shows up all the time.
So what's the big idea here? It's actually pretty simple. When you heat something up, think of all the tiny particles inside. They get a jolt of energy, start moving around way faster, and they need more space, right? They spread out. This causes the whole object size, its length, its area, its volume, to get bigger. And that fundamental tendency, that's what we call thermal expansion.
Now, here's where it gets interesting. How do we actually put numbers to this? Well, we've got three key formulas. For just length, we use this coefficient of linear expansion. We call it alpha. For a 2D area, it's beta. And for a 3D volume, it's gamma. You can see in each formula, the new size is basically the original size, plus a little extra that depends on that original size and, of course, how much you heated it up.
Okay, now this is absolutely crucial. You do not need to memorize three totally separate numbers. They're all connected. The area expansion one, beta, is just 2 times the linear one, and the volume one, gamma, is 3 times the linear one. This gives us this beautiful, simple ratio, 1 to 2 to 3. Seriously, this is a massive shortcut for solving problems quickly. So let's see this in action. Here's a question from NEET 2019. You've got 2 different rods, one copper, one aluminum, and the problem says their increase in length is, and here are the magic words, equal and independent of the temperature change. This is such a classic setup, you've got to recognize it.
So how do we break this down? First things first, let's translate the words into math. Equal increase in length? That just means delta L for copper equals delta L for aluminum. Simple. Step 2, we pull out our main formula. Delta L is L times alpha times delta T. Now step 3, we just set the 2 equations for the 2 rods equal to each other. And what do you see? That delta T, the change in temperature, is on both sides. So boom, it cancels out. That's what independent of temperature means in the math. From there, it's just algebra. We rearrange to find the length of the aluminum rod, plug in the numbers they gave us, and we get our answer, 68 centimeters.
And that whole process leads us to an amazing NEET pro tip. Anytime you read that phrase, independent of the increase in temperature, in an expansion problem, a little light bulb should go off in your head. It's a direct signal to just set L1 alpha 1 equal to L2 alpha 2. That's it. This shortcut will save you so much time during the exam, it's unbelievable. All right, let's shift gears to our next big exam hotspot, calorimetry and phase change. This is all about the movement of heat and what happens when things melt, freeze, or turn into vapor. So the whole foundation of calorimetry is built on this one simple but really powerful idea. It's just conservation of energy. In a closed system, heat doesn't just appear or disappear. It just moves from one thing to another. So the amount of heat the hot object loses has to be exactly the same as the amount of heat the cold object gains. Heat lost equals heat gained. It's that simple, really.
Okay, this is a super common mix-up, so let's make this crystal clear. Specific heat, that's the Q equals mc delta T formula, is all about the heat it takes to change the temperature of something. You're making it hotter or colder. But latent heat, Q equals ml, that's the heat it takes to change the state or the phase, like turning ice into water. And here's the key. During a phase change, the temperature stays totally constant. One formula is for changing temps, the other is for changing states.
All right, let's put that to the test with a more conceptual, tricky question. You've got 2 identical bodies, but here's the twist. Their heat capacity actually increases as they get hotter. So you take one that's at 100 degrees Celsius and one at 0, and you bring them together. What do you think the final temperature is going to be?
Now, wait a minute. I know what you're thinking. Just average them. 100 plus 0 divided by 2 is 50. And that is a trap. That little shortcut only works if the heat capacity is constant, but the question went out of its way to tell us it's not. This is a classic NEET move to check if you're really reading the details.
So what's the real logic here? Well, since heat capacity goes up with temperature, the hotter body at 100 degrees has a higher heat capacity. Think of it this way. It has more thermal weight. For every single degree it cools down, it releases more heat than the colder body can absorb to warm up by 1 degree. So the hot body basically wins the tug of war. It pulls the final equilibrium temperature closer to its side, which means the final temperature has to be greater than 50 degrees Celsius.
And that actually brings us to our final key topic for today, and this is the one that's going to help us finally crack that coffee question from the beginning. Let's talk about the laws of cooling, and specifically Newton's law.
You know, Newton's law of cooling is actually super intuitive. It just says that a hot object cools down fastest when it's really different in temperature from its surroundings. A steaming hot mug of tea cools down way faster in a cold room than a lukewarm one does. As it gets closer and closer to room temperature, its cooling rate slows right down. The rate of heat loss is proportional to that temperature difference.
Now, you'll see this law written in two main ways. There's the official calculus version, the differential form, which looks a bit scary. But for NEET, the real hero, the one you're going to use 99% of the time, is the approximation method. This formula is fantastic. It connects the average rate of cooling to the average temperature difference. This is your go-to tool for solving these problems.
All right, it's the moment of truth. Let's circle all the way back to that NEET 2021 question. That cup of coffee cooling down in 2 different stages. We now have the exact tool we need to solve it, and it's that approximation formula for Newton's law of cooling. Okay, let's walk through this. First, we apply the formula to stage 1, cooling from 90 down to 80 degrees. We plug in the numbers, and that gives us our first equation. 10 divided by T equals K times 65. Got it? Now, we do the exact same thing for stage 2, cooling from 80 to 60. That will take a new amount of time. We'll call it T prime. That gives us our second equation. 20 over T prime equals K times 50. Now for the clever part. We just divide the second equation by the first one. Why? Because that constant K just cancels right out. We're left with a simple bit of algebra. We solve for our unknown time T prime, and it comes out to be 13 over 5 times the original time T. See? Not so bad when you have the right formula. So, there you have it. We've covered thermal expansion, calorimetry, and the laws of cooling. We've even tackled some real neat questions. Now, let's boil all of this down into a clear, simple game plan for your studies. Here is your go-to formula flashcard for this chapter. Today, we really focused on the top 4: thermal expansion, specific heat, latent heat, and Newton's law of cooling. The last 2 on this list, Stefan Boltzmann's law and Wien's law, are all about heat radiation. Also super important for this chapter, so make sure you review those too. But for now, make sure you've absolutely mastered the ones we covered today. And I don't just mean memorizing them. I mean knowing exactly when to use them and why.
And to finish up, I want to leave you with a thought, something to connect the dots. We've talked about how heat makes a rod expand. But what if you lock that rod in place and don't let it expand? Well, that creates something we call thermal stress. And that should make you wonder, where else in the physics syllabus have you seen a change in one property, like temperature, create a totally different kind of property, like a mechanical stress? Keep thinking about those connections. That's how you'll truly master this exam. Good luck.